Stop chewing the blue tack.
Hello, welcome to Sensors. Today we're going to be talking about sensors and how we create computer vision on robots. Ones exactly like this. So computers use sensors. Look, have you got something to say? Cool. Sensors for robotics output a specific type of data to then be received and interpreted by the computer. All sensors see in analog. So if we're going to be doing analog, we need to convert that to digital, as computers cannot read analog. It will run through an analog to digital converter, which one of these looks like this, or at least this is the topology for it. It turns the wibbly analog into a nice stable 1-0 digital. When it comes to our sensors, it will take real world data and interpret it as data to create its own world to have vision. So we're going to be talking about ultrasonic sensors. So this man, his name is Ian, and he was the first to use ultrasound, but mainly in the conventional terms of using it to scan for pregnancy. Ultrasound is used differently in robotics, and it's mainly called an ultrasonic sensor. It works the same way that our bat does, and this list of animals that also use echolocation, it sends out ultrasonic waves and then it will return back to a receiver, and that will allow itself to project a 3D space. Ultrasonic sensors are fairly cheap, looking at about £6 for different components, and are usually, as you can see right now, why I'm underwater, are used for underwater devices, as sound waves actually travel faster through water than they do through air. The main advantages of using ultrasonic sensors are that they're very cheap, they have a decent range, and they're fairly easy to set up. The disadvantage of sonars is it can actually be day dependent whether or not your sonar is going to work properly. As the cone is 30 degrees, as in 30 degrees, this 30 degrees, not this 30 degrees, they can cross paths if the sensor receivers are too close together, because they can't differentiate between the 20,000 to 40,000 kilohertz that sonar uses, and so it can cross paths and create a false image. But at the end of the day, an ultrasound sensor will still allow a robot to maneuver in 3D space and allow itself to avoid objects. So the next sensors that we're going to talk about are cameras. Cameras are an incredibly common product. The majority of people know what a camera is. Not everyone knows how they work or how they began historically. So in 1816, a man with this long name that I'm not going to try to pronounce, he left a solution of silver chloride on his windowsill with a frame above it. The light cast it in, it hit this frame, and then it hit into the silver chloride, and the silver chloride turned out to be photosensitive, meaning that it's sensitive to light and will burn when it's in light. It then left a negative imprinted in the solution, and it all developed from there. There are different techniques then to create a full colour image, as the burn in the negative would only create a black and white image if you use the correct chemicals to develop it to have the correct colour proportions. But past the history, modern days, they use chips of silicon with microscopic photosensors on them that allow the image to be captured digitally. So the good things and the bad thing about using cameras on robotics are they are a very high quality, cheap sensor. They create a good textured image with correct light, a good or a fair distance, because cameras can zoom an incredible distance with specific lenses. But the problem isn't the quality of the image, it's the complete lack of depth perception. But also now there are mobile robots which use cameras which are fully cameras themselves. They have cameras on arms. Cameras on robotic arms, they don't even need camera crew anymore. They don't even need a camera person because the robot arm can do it. You can pay about 50 grand for a really good camera if you really wanted to, but you could get a rubbish webcam for £5 and that'll do a robot. So next we're going to talk about infrared sensors. Infrared was discovered in 1800s just by observing a prism and measuring the temperature change that was outside of the prism or outside of the visual light spectrum. There are two types of infrared sensors. There's quantum infrared sensors, which there's not a chance I'll be talking about because I just wouldn't know what I'm talking about. So we're going to stick to the other type of infrared sensor, thermal infrared sensors. So there are 3 laws for infrared. The main law we're going to be talking about is Planck's radiation law. Although Stephen Boltzmann's law and the Wien's displacement law are also important to the theory of infrared, I will be discussing Planck's radiation law. So the law states that every object at the temperature of T not equaling 0 Kelvin or absolute zero emits radiation. Everything emits infrared radiation, as far as we know right now. So to get an infrared sensor to physically work, you need preamplifiers in the circuitry. But you need to amplify the signal, because otherwise you're not going to be able to see the actual radiation itself on a graph, because it won't be strong enough. There are multiple non-robotic uses for infrared technology. There's night vision. Infrared astronomy is when you look through a telescope with an infrared detecting sensor, it will see different stars in a different shape to the universe. And so when you see huge, beautiful pictures like this, and it's like, wow, look at that universe. A lot of this stuff, we physically cannot see it because our eyes don't interpret it correctly. So robotics-wise, infrared sensors can be used on homing missiles. These sensors work on a missile by tracking a target by seeing the heat that it's emitting. Another common use for infrared sensors is everyone's favourite noise, a car beeping when you're about to hit the car behind you while you're trying to reverse. Now the problems with infrared sensors is that they weaken incredibly quickly. If you're not on a very intense source of infrared, then using it as a distance sensor from far away, you're trying to use it to map 3D space that's not immediately around it, is fairly useless. It's not going to have the same accuracy and effect as other sensors, such as the camera that has a great visual distance, even though it doesn't actually know it does, which is an incredibly important thing. Depth perception is just a very, very important thing in general, which I think people take advantage of, but on robots, very, very, very important. So the next and final sensor that we're going to talk about are structured light sensors. Most people have heard of a device using a structured light sensor system, but not many are aware with the name or the actual use itself. So one thing that uses a structured light sensor that the majority of people know about is a Microsoft Kinect. So the way that a Microsoft Kinect works is it's got 3 sensors on the front. 2 are structured light sensors and 1 is a camera. So the camera, we already know how cameras work, but a structured light sensor will shoot out, in earlier examples of structured light sensors, infrared radiation, but it's fallen out of favour because a cooler, hipper, better method of using structured light sensors is time of flight sensors. Now, time of flight sensors, they sense the time of flight, and the flight being light. Light, very reliable, so you can measure how fast it takes to get to something and measure it to create its own depth map. So time of flight is less practical for outdoor use, considering there's already visible light everywhere if it's daytime. So there's a lot more interference when it comes to time of flight sensors, but they can be very, very, very precise, which is plus or minus 4 centimeters. A time of flight sensor is also usable on most materials, surfaces, and in most environments. So now we come on to how they all work together. So as for practical uses in ultrasonic sensors, underwater exploration robots, then it's just a camera. Now for time of flight sensors, they have to have a camera. They have to have a type of camera to work, or they can't be used. So camera and infrared cameras create a model of 3D space. This is the basis for the majority of all depth mapping and trying to navigate physical space. So any obstacle avoidance robot will typically have this pairing minimum. Then you can also use a laser and infrared sensors for the heat-seeking missiles, as mentioned previously, because one will tell you how far away from the target you are, and the other one will track you to the target. When you've got cameras and lasers, we could discuss UAVs, or
UAV online.
aerial vehicles used by the military, or I suppose could be called a military drone. These can scan an area, it can create a map, and then you'd also need a camera for someone to fly it, and although it's not autonomous, it's still a robot. And so then, hopefully, if you've learned anything about how sensors work or how they go together, eventually you can go on to create the ultimate robot that would look something a little like this. Now that's perfection. Thanks for watching. Yep.